Hello, Physics 20s. I want to introduce waves today and just give you some tips on on the universal wave equation. That's the first formula we're going to learn about waves. So I've defined waves here. A wave is a disturbance from equilibrium that causes a transfer of energy. Now that transfer of energy usually goes through a medium, but it doesn't have to. Some waves can transfer through a vacuum. Most of that is electromagnetic radiation, but it is done by means of vibrations. So that's what a wave is. It's kind of a technical definition, but anytime you're taking a medium and you're disturbing it from equilibrium, you're creating waves. I use the word medium. We're going to use that a fair bit. That's just the substance or material that a wave travels through. And what you'll see with some of my animations, and I'll emphasize this, is that the medium does not travel with the wave. Okay? Now, you'll see what that means shortly. It just means that if you generate a wave, say in water, the wave is really the transfer of energy through the water. It's not like the water is moving, you know, say from your boat all the way to the shore. That water physically that's right by your boat doesn't go all the way to the shore when you're generating waves. So anyway, there's two types of waves. We're mostly going to look at mechanical waves. Don't worry about the dimensional ones so much. I mean, we'll kind of look at them in all directions. Thing is, they do require a medium to travel through. We're largely going to look at water and air for sound, but also we'll generally look at solids. We'll look at how water travels, or sorry, how waves travel through solids. When we take Physics 30, we're going to study electromagnetic waves, and that's energy waves from accelerating charges. But they do not require a medium to travel through, so that's like light and X-rays and all that cool stuff. So these notes really focus on the two that I want you to know. We really don't need to know the surface waves, although we study those, and when you think about waves, that tends to come to your mind. If you think about surfers or waves crashing on the beach, you tend to think of what we're looking at as the surface water waves. But so the two waves that we need to know are transverse and longitudinal. Okay. Now a transverse wave, we're going to break this down in just a second, but this is where the medium travels up and then down as you go from left to right, creating what we call a crest and a trough. That's in the notes a bit later. But so here, though, the particles, and you'll see this shortly, the particles are moving up and down. That's what these arrows indicate. Okay. So the medium is actually moving up and down, but the wave is being transferred to the right in this case. So what that means is the particles are vibrating perpendicular to the direction of the energy transfer. Okay. That's what sets a transverse wave apart from a longitudinal wave. And the longitudinal wave, the particles do vibrate. That's what this arrow shows. The particles are vibrating from left to right, like they're bouncing back and forth like this. And they're kind of hitting, like one of these little circles is hitting another particle in the medium. So it's imparting its energy to the next particle. And so in this case, the energy transfer is to the right in this case. So the wave is moving to the right, but the particles are also kind of moving. They are moving left and right in that same plane. So what we say then is the particles vibrate parallel to the direction of energy transfer. You'll see this is just kind of a theory. This is what separates the two. And I just noted it here, waves that are in fluids, they always are what are called longitudinal waves. So when we say fluids, I basically say any medium that waves can travel through. So we're talking mostly about water and air when we're studying fluids. So I actually want to here. Let me just pull this up so you can see the difference between the two. So here we looked at transverse waves. Let's look at this transverse wave first. Here, I just kind of blow it up. So you can see here in a transverse wave, and this is what we largely see in surface water waves. You can see that the medium is actually moving up and down. And if you want to let your eye focus on any one of these black dots, if you just focus on one black dot, you'll see that that little black dot is just going up and down. Okay. But I mean, I guess it depends on how you read this. My brain sees this as a wave moving from left to right. And that's just probably because we're trained to decipher things from left to right. So if you look at the left side here, you can see that there's a wave moving from left to right, and you can kind of follow it with your eye. So this is, again, a transverse wave, and really the only example of this that we study at length is like a surface water wave, because effectively most of the waves that we tend to come across are actually going to be longitudinal waves. But again, the medium here is not moving with the wave. The medium is just going up and down. So if we look at this one, this is a longitudinal wave. And if you can see this this gray bar on the left here, this is kind of like well, we call it a wave generator. It's a bar that's vibrating on the surface of, say, water, if we're going to look at it this way. We could think of this as a sound wave too. Like this gray line could be a speaker, and the diaphragm of the speaker that's moving, it's vibrating back and forth, and it's hitting air molecules, causing them to compress, which then compresses the air molecules beside them, and that pattern propagates outwards. There are some red dots here. If you can kind of see, I'm kind of half circling one of them here. But again, if you look at that red dot, the red dot just moves a little bit to the right and then it comes back, a little bit to the right and then comes back. So the medium itself is not moving with the wave. Like sound waves, for example, like when I yell at you, you're not being knocked over by the wind of my voice. Okay. The wave is propagating. It's a series of compressions that happen in the air molecules that eventually gets to your eardrum, and your eardrum interprets that as sound. And I guess this down here shows it as well. These arrows point at the particle, but the red arrows point at the particle, but the black arrows pointing at the wave. And we'll get into that compression and rarefaction, at least for the definition of the waves here in just a second. So actually, let me come back to that. So what causes waves? Well, it's a vibrating source. And there's one slightly different phenomenon, and that's called a pulse. If we produce half of a vibration, that tends to kind of produce a pulse. And I'll show you one of those in a bit. A pulse is kind of like, if when you're making your mom happy in the morning by making your bed, you pull up a portion of the bed sheet and you kind of create a pulse. You go up and down really quickly, and that pulse propagates through the bed sheet, and that energy kind of helps to spread the sheet out. We've all done that with a bed sheet. That's a pulse. Okay, if you just kind of go up and down. A complete vibration, though, as we'll see here shortly, will produce a complete wave, and that would be an up and a down, like above equilibrium, below equilibrium, and then back to equilibrium. So yeah, let's just go to this anatomy quick. So I think you're familiar with these terms, but we're going to use them quite a bit now. So in a transverse wave, we have a crest, which is the positive amplitude or above equilibrium, and we have the trough, which is below. And if you even look down here, I kind of highlighted this, the displacement from equilibrium up, that's called the amplitude A. Okay, so you can have a positive amplitude here for the crest, and then a negative amplitude here for the trough. Sorry, let me move that up just a little bit. Okay, so you need to know that general anatomy. Equilibrium is the state of rest where the medium would be at rest, and that's just designated here by the dotted line. And yes, the new big term that you're going to get used to is the length of the wave. Now, the wavelength is from a point in the wave, and then you follow the wave until you get back to that same point where the wave is about to repeat itself. Okay, so if I make a little space here, I mean, you can add this if you want, but we could draw another wave, okay, something like this. Okay, so here effectively, we can measure the wavelength, or it's the Greek word lambda, which is this guy right here. Okay, it kind of looks like an R, but not quite. I tend to draw mine something like this a lot of times, but that's the Greek word lambda. And we use that to represent wavelength. So very easily, a lot of times we just measure it from crest to crest. I didn't do that in this animation because I measured it from kind of the starting point here to there. But you can measure wavelength anywhere, and you'll see that. I'll show you that picture. In fact, it's right down here. I might as well just show it to you. See, wavelength, it can be measured from any point in the wave to any other point in the wave. So you see here, we've got three measurements. I can measure wavelength from there to there, I can measure it from there to there, or I could measure it from the trough to the trough. We often go from crest to crest. That's kind of the easy one because you can identify the crests in a wave pretty quick, but it's the actual length of the wave. So just coming back here to make sure I hit the rest of these. Oh yes, for a longitudinal wave, let's talk about that for a minute. Compressions and rarefactions. When you start a wave, I almost like drawing it like this. I know we attempted here in the notes, but it's not amazing. A compression might look something like this if I use a bunch of wave fronts, okay? And then after that, the waves will kind of expand out a little bit, and then they'll compress again, and then they'll expand out, and then they'll compress again. So the compressions would be where the waves are compressed, okay, something like this. And the rarefactions are where they are stretched out, okay? And so you get this pattern. Obviously, it's a repeating pattern if you continue to make the wave of compressions and rarefactions. And a finer point with a longitudinal wave is the wavelength isn't from compression to compression. It's actually from one compression, you skip one, and then you go to the next one. And that would be equal to wavelength. And that might kind of make sense here because, you know, if you look at the longitudinal wave, the wavelength is from one point here to where you have another, where you're about to repeat itself. And this first crest, might be, you know, we might say have a compression here, and then we have a rarefaction, and then we have another compression. Okay, so from the first compression to the second compression immediately, that's only half of the wavelength. We need to do another rarefaction and then another compression, and then we can get the full wavelength. Now, you don't have to worry about that too much with longitudinal waves, but if that helps you visualize it a bit, it's the parallel to a wavelength in the transverse wave. Transverse waves are really easy to decipher, though, because of their shape. A few other things we should note about waves. If you have a point source of a wave, especially a surface water wave, like if you just drop a rock in a pond, right at the point if you dropped it, you start a disturbance of the equilibrium or of the surface, and it generates circular wave fronts. Okay, so I'll attempt to sketch this. We'll look at some diagrams of this very soon. But the point is you make concentric circles that radiate outwards from the center, just kind of like an archer's target, okay? We have the bullseye and then their circles coming outwards. The very outermost part of this wave is called the wave front, or it's like the first wave front. Sometimes we call them all fronts, but it's the first, it's the first disturbance that's moving away from the point source, I guess, if you will. Okay. And most of the time we label, in fact, this is our convention. We take these lines to be the crests. Okay. So wherever there's a line, we would say, here, let me move this over if I can. I don't think I can. So the lines are considered to be the crests. So yeah, I'll have to just tuck that in there. Okay, sorry, that's a bit tight. The spaces in between the lines, those would be the troughs. So if you can follow that, you'll see that in a lot of the diagrams we're going to analyze in the near future. But we have crests and troughs inside a set of concentric circles. Okay, so I don't think the anatomy is too hard, but what we're going to look at right now is I'll go through some of the characteristics of the waves mathematically, and then I will show you a couple more animations. So all waves have a frequency, and it's measured in hertz. We would still say it's the number of vibrations or the number of complete waves per second. Okay, so we still measure that in hertz. The period is the time for one complete wave. So, excuse me, how long it takes for you to go from crest to crest, or from a compression to the third compression, basically, to get a complete wave. Okay, so these aren't too foreign to you at all. I think you'll have no difficulties using period and frequency. I already showed you this part on the next page for wavelength, which is lambda. Again, I don't think you'll have too much difficulty finding the reference points. You can go from wavelength to wavelength, or sorry, from crest to crest, I mean. Amplitude, here's the one that we'll study in just a little bit. Amplitude, this is the maximum displacement. I already showed you that back up here, okay? It's how far from equilibrium the wave is displaced. What's important to note about amplitude, though, it is a maximum displacement, but it is not affected by the speed of the wave. We're going to learn about speed of the wave right away. Amplitude is determined by the source. So if you're, and I'll show you an animation here, but if we're up, or we're going up and down here, the source is what determines how high the wave is from equilibrium. It's not affected by the speed. The speed of the wave is determined by the properties of the medium. So let's go to that right now. In fact, let me just compress that. The speed of the wave depends on the elasticity and the density of the medium. I just like to think of that as the properties. Okay, the properties of the medium. So how dense it is, how hot it is. We could also add temperature. Okay, the temperature of the medium can change the speed of the wave. Don't worry at all actually about this formula, although it probably makes sense to you. The elasticity, how elastic the medium is, how stretchy it is, and also how dense it is. Those two variables affect the speed. The one that we're really going to focus on, though, is the very first formula we ever learned in Physics 20, and that's this guy right here. Woohoo! Velocity is equal to the distance traveled divided by the time. Now, to make the universal, what's called the universal wave equation, we actually just change the properties a little bit of distance and time, and it's not too bad. The distance that we're talking about is going to be the wavelength. Okay. Yes, a wavelength is 2 times the length of a pulse, because remember, a pulse is only half of a wave. That's kind of like a compression. A pulse and a compression are like half a wavelength. But anyway, so we just replace d here with wavelength, and we replace the t, the time, with the period. Okay, so the period and lambda get kind of put into this new formula for the speed of a wave. Most of the time, though, we don't deal with the period of the wave, like how long it takes for the wave to be created. We use the reciprocal of that. If you remember, frequency is equal to 1 divided by the period. I showed you the equation there. So if we insert that into the equation, we now get velocity equals frequency times wavelength. Now, I know here they said wavelength times frequency. I mean, it doesn't really matter. It's the same. I'm just showing you that on the formula sheet, I wrote it like this. The velocity of a wave, and we call it the universal wave equation. It equals the frequency of that wave in hertz multiplied by the wavelength. In typically it's meters, but I mean, if you, depending on your velocity, you can get meters per second or centimeters per second, whatever. Okay. So yeah, the frequency needs to be in cycles per second. And typically the wavelength is measured in meters for the most part. And that will give you a speed in meters per second. Okay. So, yeah, before I talk about this last one, let's go back to these animations so I can show you some of the properties of the waves. So here's a basically a string, and here is on the left here is my source. Okay, and I'm going to start by generating a pulse. The tension, we're just going to put the tension here. If you can see that, it's just in the middle. Actually, we can only go, I don't think I can go in between. Yeah, I can just have in the between, so it doesn't matter. So anyway, here we go with a pulse. So you can see my pulse. I started it, and this is in slow motion. I guess I should maybe do it in high speed here for you so you can see it. But a pulse is just the up and down movement, okay? Let's just go at normal speed here so you can see it. Up and down, woohoo, there she goes. Okay, there's you making your bed in the morning. That's a pulse. There are some other properties we can generally know about. Damping is where some of the energy gets lost in the transmission. So if I turn on the damping, see, look at that. The wave pulse kind of loses energy as it moves down the way, and eventually it dies right out. Okay? Now, I'll maybe keep it in the middle. If we change the properties of the medium, we will change the speed of the wave. And we won't do any measurements, but I just want you to watch. When the tension's low, okay, you can see the wave. Oh, here, let me take off the damping so it just keeps going forever. Okay, so you can see kind of just qualitatively, you can just see how fast that pulse moves down this string. If I make the tension high, though, this is, imagine having a spring, and if you make it really tight, or even a piece of string, I should say, if you make it really tight, and then you create a pulse, yeah, it goes very fast. Okay, so the velocity is affected by the properties of the medium, but not the amplitude. See, this amplitude is 0.06 or 0.68 centimeters. That amplitude is the same if the medium is low tension or high tension. I have the same amplitude. So that's what I mean by amplitude. It's determined by the source. Okay. Now, let's actually turn on an oscillation here. Let me restart this. Okay. And let's keep, let me turn on the slow motion here, and let's just run it here. So this is, oh, you know what? I'm going to make that a little bit bigger. Here, let's turn the frequency down. That was a bit high. So we'll drop the frequency here. Let me restart this. Okay. So in slow motion here, now we have a complete wave that's being generated. I'm not generating a pulse. I'm not generating half a wave. I'm generating a complete wave. And I'm just going to keep generating them. So I generate wave after wave after wave. The medium, of course, is moving up and down, as you can see, but the wave moves from left to right. And here we can get all the properties of the wave. So as I'm running it here, you can see the crests and the troughs. And we are generating waves that are moving at a certain speed. Now, because I have the frequency, I would have to measure the wavelength, okay? So yeah, I'm just using my ruler here. You know, we could measure from crest to crest. So put the 0 right on one crest. Oh, look at that. It's pretty much a centimeter or close to it. Looks like it's a little bit less because it doesn't stay right on the centimeters, and I'm just making this up. So if we got the wavelength, we measured the wavelength, it's probably 0.9 or something centimeters. We've got the frequency down here, so with the frequency and the wavelength, we can determine the speed, and it's that simple of a calculation. Notice too that I can change the amplitude just for fun. So now I really punch the amplitude up. But look, you can see the two waves side by side. Like the leading waves there have the same wavelength as the trailing ones, because all I did was change the amplitude. I didn't change the frequency. I didn't change the wavelength. I just changed the amplitude. So the amplitude is just greater, but I didn't change any of the other properties. Now, if I start changing the frequency, then that's going to affect the velocity. Okay, so actually, let's just put the frequency up to quite a bit higher here. Okay, so the if the wavelength, or sorry, if I change the frequency, oh, that just looks kind of messy now. If I change the frequency, that changes the wavelength as well. See, now the wavelength is much less. And then if I have a really low frequency, okay, now look what I've done to my wavelength. Okay, so actually that one looks a lot better. Obviously I've slowed it right down. Yeah, if we go to normal speed and just kind of clean things out, there you can kind of see it. So if I change the frequency, I'm going to change the wavelength and vice versa. So that's probably about as much. Oh yeah, I guess I could show you the tension here. Look at that. If I if I make the tension very high, now that affects the speed big time. It also affected the wavelength. But if I change the medium so that it is not very tight, I change both again. Okay. So anyway, all these variables kind of come into play, and we're going to look at how they interact with each other. The one example I do want to show you is this one here, and this has to do with a water wave and how a water wave changes as you go from deep water to shallow water. Deep water, what you need to remember is that water travels faster in deep water, and that's what this emphasizes right here. And that's also shown. I'll maybe keep these in red so you can follow it. Okay, that velocity shows the velocity in water, and the wavelength is from crest to crest. We have like a straight wave generator here, if you can see that. Okay, so the waves are moving away from that, and this straight wave generator is just vibrating back and forth. What happens though in this tank is there's a barrier. So, and it's basically just a change in depth. So from this point forward, the water gets very shallow, and we don't know how shallow, but it definitely changes from deep to shallow water. In shallow water, what happens is the speed decreases. So actually, I maybe should have changed colors here. So this, if you'll note, this arrow here is not as long as the comparative V1, and wavelength number 2, you can see, has gotten smaller. So the phenomenon here is that you can see the velocities are proportional to each other, and so are the wavelengths. The wavelengths get shorter and the speed gets shorter. But what's really cool about these is that in this case, the frequency stays the same. The frequency F stays the same. And without an animation, it's maybe hard to kind of visualize this. But what I'm saying is the number of waves being generated per second, that's determined by this straight wave generator down here. And that number doesn't change. So if I'm generating 10 waves a second, or 10 hertz, 10 cycles per second, that's happening that's happening everywhere. That's happening in the deep water, and it's happening in the shallow water. This paragraph here looks to emphasize that as a wave moves from one medium to another, the frequency does not change. The frequency of a wave is always the same as its source. So what does change, though, is the wavelength and the speed. So what I want you to be prepared of is how we use this universal wave equation. What we can do is we can say velocity 1. Oh, wait, here, let's do that in the same, let's keep it in the same color here so that it lines up with what we already did. So we'll say that velocity 1 is equal to frequency times wavelength 1. That's what's happening in the first medium. In the second medium, we have a second velocity times a frequency times wavelength number 2. Okay? And that's what I'm showing you right here. So velocity 1, velocity 2, wavelength 1, wavelength 2. What's really cool though about this is because we've emphasized that the frequency is the same, that means that this frequency and this frequency are the same. Okay? So they don't change. So effectively then we could say this, we could say velocity 1 over wavelength 1, that's going to equal the frequency. And we could also say that the frequency over here is going to equal velocity 2 over wavelength number 2. Because these frequencies are the same, we can just kind of cut them out, and we basically can get a new formula. Now, this one's not on your formula sheet either, but I just want you to see that you could simply say velocity 1 over velocity 2 is equal to wavelength 1 over wavelength 2, okay? Or any other configuration that you want. You could just stay with this original one here. Velocity 1 over wavelength 1 is equal to velocity 2 over wavelength 2, okay? But yeah, simplified, I brought it down here for you, okay? Now, this actually it will lead us into studying more of the properties of waves, which I'll get to in the next set of notes. But for right now, I want you to practice using the universal wavelength, the universal wave equation. And the math isn't too bad at all. I think you'll have no problems staying on top of it. Just be prepared, though, if you have a pulse. Actually, I'll maybe do number 1. I'd like you to do number 1 and 3. And yeah, I think just 5, 6, and 7 for now. I'm going to post the answers to all of them, though, in case you wanted to try the remaining ones. But I think these give you a good snapshot of the math you would need to handle these questions. Okay, so I'll do number 1 with you, and then I'll just post the rest of it. So if you generate a pulse that's traveling at 5.3 meters per second, if it helps you can draw a little picture. I think of a pulse as just the disturbance up and down like your bed sheet. Okay, it's moving to the right, whatever, but it tells you that it's traveling at 5.3 meters per second. And it says the time that it took to generate that pulse is 0.640 seconds. So that would mean the time that, if you can see it in the drawing here, if my hand is at the end here, it would be as long as it took for me to go all the way up and then back to equilibrium. That time would be 0.640 seconds. Now, while my hand's doing that, as you saw in the animation, the wave starts to move away from me. It starts to go down the spring. And it would cover a distance of the distance is the wavelength. That's what I don't know. Okay, so how could I determine that? Well, if you know that velocity is equal to distance over time, the distance, of course, in this case will be the length of the pulse. So it's technically not a wavelength, but it is a distance. So very simply then, I would just take my velocity, which is 5.3 meters per second, and I would multiply that by the time of 0.64 seconds. Okay, so that gives me 3.39 meters. And that would be the distance that the pulse would have, or that's how long the pulse is basically, because that would be the shape that would just move down the spring. So number 1B then, does the speed of the pulse affect its amplitude? Ooh, this is the theory. So what I'm hoping you're going to see here is, does the speed affect the amplitude? The answer is no. Amplitude is not affected by the speed of the wave. Okay, amplitude is affected by the source. Okay, so the source of the wave that's being generated. So anyway, I will let you try the other questions, and you're just going to be applying either the speed formula or the universal wave equation using period and or frequency. So make sure that your units are in the right form. But other than that, I think you guys can tackle that one. So I will post the answers to this shortly. So here we go with waves.